Forming chemical bonds. Okay, so in this topic, we're going to talk about how atoms come together to form compounds and the different kinds of bonds that hold these compounds together. So there are three basic bonding schemes. You either fall into the category of ionic bond, we get an electron transfer and we get electrostatic attraction between the ions. Covalent bond, where the atoms are trying to take electrons away from each other, but in order to lower potential energy, they share. And metallic bonding, which is strictly for metals. It's a type of covalent bonding where we have delocalization of electrons throughout the crystal. We're gonna hold off on that one. Right now, we're just going to talk about ionic and covalent bonding. So why do atoms form chemical bonds? Well, the answer is to lower potential energy. We've talked about kinetic energy versus potential energy earlier in the course, right? Potential energy is energy due to position. So in chemistry, potential energy is about the electrostatic attraction between protons and electrons. So the proton in the one atom is attracted to the electron in the other atom and vice versa. So it would take energy to keep these two particles apart. They are attracting each other. That's what's meant by high potential energy. As I let them come together to maximize the attraction between the protons and the electrons, the potential energy drops. And we get to a point where we've maximized those attractions and minimized repulsions, right? If I try to shove the atoms too close together, you notice that the potential energy goes right through the roof. It's because you're pushing them closer together than they want to be. So this is what bonding is all about, lowering potential energy. So one way to lower potential energy between the atoms is to have a transfer and then an electrostatic attraction. It's usually between metals and nonmetals, right? So we've done this before, right? Metals lose electrons in chemical reactions to the nonmetals. All right, in order to describe this, we're going to get into this describing bonding. We're going to get into this convention called Lewis dot symbols. A Lewis dot symbol is when you take the symbol for the element and you put a dot for every valence electron. So if you're in group 1A, you have one valence electron. If you're in group 2A, right, for beryllium, you got a helium core and 2 valence electrons, and so on, right? 3 valence electrons for group 3A, 4A, 5A, 6A, 7A. And when you get across to 8A, right, you've completed what we call the octet. You can't put any more outer electrons before you start another energy level. So the main group elements, right? You look at the number and you've got the number of valence electrons, so you can draw the Lewis dot structure, the Lewis dot symbol. So our concept of what happens when lithium finds fluorine, right? The lithium atom has one valence electron. It has a hard time holding on to that valence electron. So it loses it to the fluorine. The fluorine has one more space in that 2p to take an electron. So the electron is transferred. Now what you're left with is a lithium cation lacking its outer electron, and you've filled the outer level for fluorine and made fluoride. So now the lithium cation has shrunk, right? Got this tight little cation. You've puffed out the fluorine atom to form fluoride. And now there's an attraction, electrostatic attraction between the cation and the anion. And these ions surround each other in such a way to try to maximize those attractions. This is what's called a crystal lattice. This is why ionic compounds are always solids at room temperature, right? They form this crystalline structure to try to maximize these attractions between the puffy green anion and the tight positively charged cation. All right, lattice energy. All right, the energy that is released when you form that crystal. Looking just at the energies, right? I mean, from the last topic, we realized that, hey, it takes energy to ionize something, right? Ionization energy. So we always talk about sodium, wanting to give up its electron. Well, no such a thing. It costs a lot of energy to knock an electron off of sodium, right? It costs you 496 kilojoules if you want to remove a mole of electrons from a mole of sodium atom. As far as chlorine goes, right? Chlorine's a taker. So chlorine's the best taker on the chart. If chlorine's going to react, it's going to release 349 kilojoules. So I strictly look at the energy required to make sodium versus the energy release when chlorine takes an electron. You're putting in more energy to form the sodium ion than you are getting a release when the chloride ion forms. So there's got to be something more to this than just, sodium wants to give up its electron and chlorine wants to gain. We know this is an exothermic reaction. We've seen the demo, right? You put sodium with chlorine, it's a big explosion. So why? Why the big exothermic reaction? The answer is the lattice energy. Once you form the cation and the anion, right, the sodium cation, the chloride anion, they attract each other according to this law, Coulomb's law. Q1 represents the charge on the cation, Q2 represents the charge on the anion, and D represents the distance between the cation and the anion. So if you have small ions with big charge, what this equates to is a big lattice energy, E. So that's what drives ionic compound formation. If we have a large lattice energy, a big release, when the cation and the anion surround each other, we get an ionic compound. Again, this is what drives ionic compound formation, right? You have a release of energy. So lattice energy has a negative sign. It's exothermic. So if I look at different lattice energies for the different atoms, right? One that jumps out to me is magnesium. Right, we've done this demo, magnesium oxide. Oh, hide your eyes, right? You're going to burn your retina from all the energy being released when I react magnesium with oxygen to form magnesium oxide. That's because it has a big lattice energy. If I compare it to something like cesium iodide, right? It's much lower, right? You're only releasing 600 kilojoules as opposed to 3,795 kilojoules. So the answer is why? Why the big release? Answer, according to Coulomb's law, we have a big charge, a larger charge on the magnesium ion, +2, a larger charge on the oxide ion, -2, than cesium or iodide, right? And they're smaller. Magnesium ion and oxide are smaller ions. So small ions, big charge, big release. Notice that these are positive values. They're written as positive values in this chart. That's because of the way they measure lattice energy. It's much easier to put energy in to expand the solid, turn into the gas phase, and recognize that would be the same energy release when the ions came together to form the lattice. But don't be confused. Lattice energy is exothermic. All right, the Born-Haber cycle is just a way of adding up the energies to get the energy of reaction. So if we have lithium solid, right, lithium metal, just like sodium, right, gives up its electrons to fluorine gas to form lithium fluoride, and I'm going to get a big release here, 594 kilojoules. The first thing I have to do if I'm going to have this reaction occur is I've got to prep lithium so that I can take an electron off of it. Well, that's going to cost me energy. I've got to put energy in to go from lithium solid to lithium in the gas phase, right? Subliming lithium. Next thing, I've got to knock that electron off. That's going to cost me a lot of energy. I've got to put in 520 kilojoules to knock an electron off of lithium atom to make lithium ion. All right, so now I've got the lithium cation. In order to get the fluoride anion, first thing I got to do is break that fluorine-fluorine bond. The bond dissociation energy of fluorine is 75 kilojoules. You got to put that in to break those two fluorines apart. So now I've got the fluorine atom and an electron, right? To put the electron onto the fluorine atom is going to be a releasing process. So I'm going to release 333 kilojoules. Now you look at this, right? I've been putting in a lot of energy. I'm only releasing 333 kilojoules to make the fluoride ion. So where's the big release where I get, almost 600 kilojoules being released? The answer is Now that I have the lithium cation and the fluoride anion, the attraction between those will cause them to solidify, and the big drop in energy is the lattice energy. So lattice energy is the driving force behind ionic compound formation. If you don't have a big enough lattice energy to justify, um, an ionic compound, you're left with some sort of sharing situation. So how much energy you have to put in to make the cations versus how much energy is released when you form the lattice, right? If you don't have a big enough lattice energy, you're not going to get an ionic compound. Now, for example, if we look at aluminum, right? Aluminum metal, right? Shiny metal, aluminum loses electrons in chemical reactions. This is the way we always look at aluminum. If I react 3/2 of a mole of iodine with 1 mole of aluminum to make 1 mole of aluminum iodide, notice I've got to form an aluminum with a +3 charge, right? That's how I get 3 -1 iodides to match up with it. That's going to cost me a lot of energy, right? Well, first of all, this is exothermic. When I react iodine with aluminum, do the demo in class, it's an explosive reaction. You're going to release a lot of energy, exothermic. So when I look at the energies required to form the aluminum +3 ion, right, there's the first ionization energy, 580 kilojoules, the second ionization energy, 1,815 kilojoules, the third ionization energy, 2,740 kilojoules. When I add those up, it's just too high an energy barrier to justify any kind of lattice energy that's going to come off of this. Yeah, you got a +3 charge, but you're just not going to get a +3 charge in the we deal with like Coulomb's law. Oh, it's highly charged, right? Maybe it's small. Maybe it'll be justified in terms of forming an ionic compound. And the answer is no. In the end, you don't have this. You don't have aluminum ions and iodide ions. You're left with a sharing situation. So chemistry is complicated. We talk about aluminum iodide, right? We don't call it aluminum triiodide, right? Aluminum's a metal. No. In this situation, it's going to be a sharing between the iodine and the aluminum. That's the only way you can justify the energy here. It's just too much energy to form that aluminum +3 ion. So it's a sharing situation between aluminum and iodine. It's not a transfer. Lattice energy, that's what drives ionic compound